Okay, Calc students, so we're going to take a look at the second part of section 2.1. Okay, so here's what the objectives were. Last time we did the meaning of differentiable, the different ways of writing the derivative, f prime or y prime, probably the easiest way. And actually, that's what they did next two steps. Graphing, given the graph of the derivative, or graphing the derivative given the graph of the original function. That's what the one we're going to work on this one right here primarily. Look at one-sided derivatives and then graph the derivative from your data. Okay, so a little review. Remember, here's how we get analytically or algebraically, here's how we get our derivative function. We do all the steps that's provided for this, okay? Quite a bit of work, but you can do it. So now, what are the relationships between the graphs of the derivative and its original function? Okay, so what we're doing is we're looking at the slopes. The f prime is the graph of the slopes. Okay, and we're going to estimate them by using 2 points that are really close to one another. Okay, so if we had a table of values, we'd have to find slopes between, say, -3, -2, -2, -1, -1, 0, 0, 1, 1, 2, and so on. Okay, now actually what we have are discrete points. Okay, and it will not give us a continuous function with that discrete points, but we're going to look at it. We're going to look at a scatter plot and actually find the slopes between them. Okay, then we're going to use the curve to get an idea of what the derivative is visually. So we've done it algebraically with the definition of a derivative. Now we're going to look at it graphically. Okay, so let's take a look. So y equals x squared. There's the graph of it right there. I want you to draw several tangent lines and estimate the slopes. So let's start way over here. I think you'd have a tangent line looking about like this. You can see my cursor going up and down there. Okay, that's what this line is here. It's tangent at about a -2 or -3. But more important, what's our slope? It's really negative. Okay, not quite vertically negative, but it is really big number negative, if that even makes sense. Now, as we move in closer to the origin, what's going to happen to our slope? Well, it's still negative, but we're getting closer and closer to 0. Now, what happens at the bottom of the bowl? Our slope is 0. And then if we start moving up the sides, like at x equals 1, x equals 2, and x equals 3, you'll notice that the line is getting steeper and steeper, okay, but it's positive. So when we go to graph that, it's going to look something like this. That's the graph of the original function and the derivative. Now, why is it negative? Because down here, remember the slope was really negative, so that's really negative down here. Whatever that number is, it doesn't really matter, okay? As we get closer and closer to it, notice that the slope is getting lesser or closer to 0, okay? Getting more flat, I should say, not less. Getting more flat. Right at 0, our tangent is 0. That's why it goes through the point 0, 0 right there. And that 1, we can just identify, well, it's about a positive slope. But as we get bigger and bigger for your x values, notice your tangent value gets more steep. And this is the graph of our slopes. The dark line there is the graph of y prime, or our derivative of y. And we're only graphing the slopes, remember. Okay? I hope that makes sense. Got to think about it a little bit. Okay, just remember you're riding a skateboard down this. The skateboard is really pointing downhill. That's a really big negative number. But as we get closer and closer to it, it's getting to be closer and closer to a horizontal line, which means our slope is 0. That's why this function starts really negative and gets closer and closer to 0. Okay, and then as we go from 0 to a positive, notice our skateboard starts out fairly flat and then it starts to go uphill again. Okay, so at 0 it looks like this, and then it's going to go uphill after that. Okay, when we go and look at it. Now let's try another one. Y equals negative quantity x minus 1 squared. So now we've taken a parabola, we've flipped it over, so it's going to look like a bullet shot up in the air, moves up in the air, and that's going to come down. Okay, and then we have also moved it over to the right one, x plus 1, right there. So there's our graph. Now, if I pick a point like -2 or -3, there's my tangent line. What's the slope on it? Well, I can't really tell, but I know it's pretty steep. So it's going to be a pretty big positive number. It's really positive slope. Okay. Like, I don't know, 5, 6, 7. Okay. Now, the next one over, if I move closer to the vertex, notice the line starts to flatten out a little bit. It's still positive though. Now, when I get to the very vertex of it, then my slope is going to be 0. Okay. At x equals 1. And then what happens when you go down the other side? Your slopes are going to be negative to get your answer. Okay, so really big positive, closer and closer to 0, and then closer and closer to a really low negative number. So what's that going to look like for the derivative? It's going to look something like that. Notice at the 0 point, that's where we cross the x-axis there. Okay, at x equals 1. So if you're throwing something up in the air, it's going up, it's going up. What's the speed at the very top of the hill or the velocity? It's 0. Because then afterwards, the gravity starts to pull it down and then goes faster and faster as it pulls it down. Gets to be more negative and more negative. Okay. Again, use your pencil for the tangent line and look at your slopes for each one of those points that you have. Start on the left-hand side and go up. And every time you have a hilltop, or you could have a valley, okay, y equals x squared, you have a valley at the very bottom of it, at the vertex. Here, our vertex is at 1, so we know that it crosses the x-axis at 1. If I were to move this whole thing over here to about 7, then that line would follow, and it'd be a straight up straight negative sloped line right here, but it would cross the x-axis at 7 because that's where our vertex is. If you go to think of the vertex, okay, so think of it like riding a skateboard on this thing. Which way is the nose pointing? It's pointing up. It's pointing up. When you get to the top, it's pointing 0 because your skateboard's got a 0 slope, and then it's going to go point down, which is more and more negative. That's what the derivative is going to look like. This is how to graph it graphically. Okay, the derivative is graphically done this way. Okay, a little bit later on, we'll get into finding the exact answer for it. Okay, and then we have different rules. We have a quotient rule, we have a product rule, we have a chain rule, all different types of rules to use, depending upon what kind of function we have. Okay, so that's looking at the graph of the derivative. Now, we also have one-sided derivatives. That means you have a point, what happens to the left of it, and what happens to the right. So what happens to the right is called a right-hand derivative at A. What happens on the left is called the left-hand derivative of A. Okay, so on the right-hand derivative, h is positive, so we've got a plus h. If we have a left-hand derivative, if I can move my picture out of the way, okay, I'll move it up then. If h is negative, b plus h, which is actually b minus h, and you're coming in from the left-hand side. And that's why we have a 0 plus and a 0 minus. So you're just looking at it from two different sides, coming in from the left and the right. If they don't equal, then at that point, it does not exist. The derivative does not exist. Okay? So let's go through this. Let's go try one. They could be defined at any point, or they don't have to be. Let me move my picture. There I am. Okay? It just depends at what point. Okay? If you have both the left and the right-hand derivatives are the same, then it's equal at that point. Okay? Here we go. Let's try one. Look, the following function has left and right-hand derivatives at 0, but no derivative there. So you got a piecewise linear. Okay? So when x is negative or less than 0, we use negative x. When x is greater than or equal to 0, we use positive x. If I find the slope, okay, and I'm approaching it from the left-hand side, so I'm going to use the top equation or the top function part, negative x. So the negative of 0 plus h minus f of 0, which turns out to be 0, all divided by h. Okay, you get negative h divided by h, which turns out to be -1. So it's got a slope of a -1 when you're to the left of 0. If you move to the right of 0, you do the same thing, except now we're going to use the bottom function, and then you get a slope of 1. So does it exist at 0? No. The derivatives are not equal at x equals 0. The function does not have a derivative at x equals 0. Okay? That's what we're looking for. That's how you do one-sided derivatives. But they both have to equal when we do that, when we go through and do that. Okay? Your homework is a worksheet. You've got a few problems and then a few book problems to do. Okay? There's not a lot, but I think you'll do fine. Good luck on it. If you have any questions, come and see me during SRB. Okay? Thank you very much, folks. We'll see you later. And we'll see if I can close this out.